Welcome back, focused learners. Today, we've got an absolutely fascinating explainer lined up for you. We're going to decode the fundamental mechanics of nuclear energy. Literally, the very forces that hold the universe together and, well, what happens when we manipulate them. If you've ever wanted a clear, no-nonsense breakdown of how humanity harnesses the atom, you are in exactly the right place. We're diving right into the differences between the two heavyweights of atomic physics, nuclear fission and nuclear fusion.
So think about this for a second. What actually connects the power lines running through your city to the stars shining in the night sky? On the surface, they seem completely unrelated, right? One's a product of human engineering, and the other is an ancient cosmic phenomenon. But at the atomic level, they're really just two sides of the exact same coin. Today's explainer is all about that dichotomy, earthly power versus cosmic power. It's a tale of two reactions, breaking things apart and smashing things together, both of which unlock amounts of energy that are honestly kind of hard for the human brain to wrap around.
But before we split these two processes apart, we need to understand the one universal rule that makes both of them possible. You definitely recognize this equation, right? E equals mc squared. Albert Einstein's famous formula. But what does it actually mean for us here? Basically, the absolutely crucial point is that energy and mass are interchangeable. Mass is really just super concentrated energy. So in both of the nuclear reactions we're going to explore, the end products actually weigh a tiny bit less than what we started with. That missing mass hasn't just vanished into thin air. It's been converted entirely into a tremendous amount of energy. Keep this equation in the back of your mind, because it is the engine driving the whole shebang.
Okay, let's dive into this. Part 1, nuclear fission, or what we can call the Great Split.
Now picture a highly engineered clinical environment bathed in cool blue tones. That's usually where we find fission happening today. By definition, fission is the splitting of a massive atomic nucleus into smaller fragments, which in turn releases a tremendous amount of energy. You start with this massive clustered central atom that's just sitting there, highly unstable, right before it forcefully fractures and sends energy shooting out.
Let's walk through exactly how this builds step by step. Step 1, we start with an incredibly heavy, massive nucleus, specifically uranium-235. To kick things off, a single neutron is fired directly at the uranium-235. It's kind of like a cue ball breaking in a game of billiards. Step 2, the atom absorbs that neutron, becomes completely unstable, and snaps. It splits into smaller fragments, specifically barium and krypton. But here is the absolutely crucial part, step 3. When it splits, it doesn't just release energy, it also shoots out more stray neutrons. Those new neutrons go on to hit other uranium atoms, which then split and release even more neutrons. That right there is the chain reaction. It's a geometric progression that scales up almost instantly. And because of that chain reaction, fission has immense practical applications for us here on Earth. But, it's a bit of a double-edged sword. If we carefully control the chain reaction, by absorbing some of those extra neutrons, we get nuclear power plants. The steady heat released by the splitting atoms boils water, creates steam, and spins turbines to power our cities. But if we let that chain reaction run completely uncontrolled, with every splitting atom triggering multiple others in a fraction of a second, we get the devastating, instantaneous energy release of atomic bombs. So, fission is incredibly powerful, but for sure requires extremely careful human management.
Which brings us to our next chapter. Part 2, nuclear fusion. The cosmic joining of light elements.
Where fission was all about breaking things apart, fusion is the exact opposite. Think of a dramatic shift, away from the cold blue of an engineered reactor and into a chaotic, intensely energetic environment filled with fiery oranges and reds, a star-like environment. Fusion is the combining of light atomic nuclei to form a heavier one, and this process releases even more energy than fission. But to make this happen, things have to get unimaginably hot.
So let's break down the mechanics of this cosmic dance. Step 1. Instead of massive uranium, we take the absolute lightest elements available, specifically isotopes of hydrogen known as deuterium and tritium. Now step 2 is the really hard part. Because atomic nuclei naturally want to repel each other, you have to apply extreme temperature and immense pressure to actually force them together. We're talking millions of degrees here. Step 3, when they finally smash together and fuse, they form a new, slightly heavier atom. Now, a quick note for the eagle-eyed learners out there, if you ever happen to spot a quirky little typo in a diagram labeling the resulting core as helium, make no mistake, that is helium being formed. When these light isotopes fuse into helium, an astonishing amount of energy is released along with a stray neutron. Inch for inch, atom for atom, fusion yields significantly more energy than fission.
So where do we actually find this happening? Well, just look up at the daytime sky.
Fusion is the engine that powers the sun and literally all the stars in the universe. The immense gravity of a star provides the exact extreme temperature and pressure needed to naturally smash hydrogen atoms together continuously. Down here on Earth, though, mastering fusion is basically the holy grail of physics. It represents a future, limitless, clean energy source. Why? Because unlike fission, which leaves behind long-lived radioactive waste, the primary byproduct of fusion is just harmless helium gas. Plus, its fuel, hydrogen, is ridiculously abundant right in our oceans.
All right, it is time for the ultimate energy showdown. Let's compare these two directly.
The key differences here really tell the whole story. Fission is all about splitting. We take massive, heavy atoms like uranium and literally shatter them using a self-sustaining chain reaction. Fusion, on the other hand, is entirely about joining. We take incredibly light atoms, like hydrogen isotopes, and forcefully merge them, which takes star-like extreme heat and pressure. It's highly ironic, isn't it? Breaking the heaviest things in the universe apart releases immense energy, but taking the lightest, smallest things and smashing them together releases even more. Both operate under the exact same fundamental law of E equals mc squared. Converting a tiny, tiny loss of mass into a massive gain in energy, they just go about it from completely opposite ends of the atomic spectrum.
Today, we heavily rely on the great split, fission, to power portions of our grid. But the great joining, fusion, is on the horizon. The scientific community is inching closer and closer every single year to building reactors that can sustain star-like conditions right here on Earth without consuming more energy than they actually produce. So I want to leave you with this thought. If we can finally master the power of the stars, creating limitless, clean energy from seawater with zero long-term radioactive waste, how will that change the future of our planet? It's an absolutely incredible concept to ponder. Keep learning, keep questioning, and I will see you in the next explainer.